Yeah, we have collected the questions and categorized into these topics: soil, sponge and carbon, impact on climate, hydrology related, urban agriculture, uh, and
Okay.
some microbes.
Okay, so if you just read the
Yes.
question out, because that way, and just get it down to the core question.
We have selected some important questions. In the interest of time, we cannot deal with everything.
Of course.
So in arid areas with very high temperatures, soil biological processes are very slow. How to deal with this problem?
Yes, very important. You see, when it gets very hot, then obviously that kills the microbes in the soil. You see, life basically slows down, most life above 38 degrees centigrade. You know, things start getting very, very difficult. And so as we sort of said, I think we've taken away, but we need 365 days green. Here we are. We need to keep things protected and moist, and then they stay cooler. And so it is absolutely critical, particularly in desert country, dry country, that we keep plant cover, and that's what Dee was talking about, right? And remember that beautiful photograph she started with here in South Africa was the arid, overgrazed, degraded landscape, and here was the grassy savanna. And so it's very important in arid countries to keep protective soil covers, because that will keep things cooler. But definitely once soil temperatures go much above 40 degrees centigrade, then life becomes more difficult. And so the first step is, yes, protecting the soil. That's why we have, or nature puts trees in arid areas. The prosopis, weeds that you have in your dry, arid hills and slope, you see them as a weed, but they are actually extremely valuable in shading and protecting those soils and stopping them from going too hot, and keeping life in those soils.
Next question is about in dry lands when the relative humidity is about 20 to 30% only, and with the previous year being drought year, how do we harvest the atmospheric water?
Right.
In 3 years of drought continuously, how does the water cycle behave, and how do we go for PMDS?
Right. Again, important question. Obviously, the relative humidity in arid areas is less than in moist areas. So where I said there's up to 50,000 parts per million of water in the air, commonly in normal areas, it might only be 20,000 parts per million in arid areas. But that's not the issue. The issue is that plants are still harvesting those water molecules through absorption, through condensation. So it keeps on going. It's a little bit less. You may not get the same yields of water, but every drop of water that you do harvest is 10 times more precious, because it is an arid environment. And so if you get a little bit more water, it's important. As I said earlier, I think 1 to 2 millimeters of fog dew harvesting per night. We have surfaces in these arid desert areas that can harvest up to 1 liter of water per square meter per night. Okay, so the physical process still applies. You may be able to get less water, but every water drop is 10 times more precious.
And one farmer's question is, my farm is in rain-fed, rain shadow area.
Yes.
How to overcome that effect?
Yes. Okay, you are in a rain shadow area, which means that you have a mountain, windward, which is in a sense stopping the water landing. So again, it's critically important that you conserve every bit of water, so continual green plant or keeping green cover. But again, would like to see your land because you can't prescribe this. But I would think trees, shelterwood trees, scattered trees as in a natural savanna become critically important in those rain shadow areas because they are things that slow down the wind speed, slow down evaporation, and it is actually the wind scouring desiccation effect on soil surfaces where we are losing 80 drops out of 100. Remember we talked about here in India it was 70%, 70 drops evaporating. So if you have those arid zone trees preventing that wind scour, that evaporation, that will help. As a bigger statement, look, there are different extremes in landscapes. There's different stresses in landscapes. But as we said to the last question, the more stressed your landscape, the more critical are these protective measures. And even if you get less rain per measure, every drop is so much more precious. So it's it's not the quantity, it's a relative benefit from that rehydration strategy. So, yep. Good.
What are the different emissions from natural farming and chemical farming? And also how does anaerobic conditions affect rate of decomposition?
Right. Thank you. Very good. And in a way, this is what we've been talking about with the ABC. Okay, when you said what are the emissions from chemical farming, we've already just discussed that. It is oxidizing massively, losing up to 5 to 10 tons of carbon per hectare per annum back to gas, often oxidizing 120% of A. So industrial farming has really been a massive oxidative process, and as a result has turned large areas into dry lands and deserts. The 5 billion hectares of man-made desert and wasteland that we've created on the planet. By contrast, natural farming, zero budget natural farming, because it's putting more carbon into C, it is generating dividends D, which are generating these 10-to-1 synergies. So even a small contribution to C can have a profound effect in basically reducing emissions, because not only are you reducing emissions, but you're increasing the drawdown of CO2 by the increased A. See, because you've got more water, you've got more nutrients, you can have higher productivities, which are actually drawing down CO2 from the air. So this is where you get that synergistic effect, and quite frankly, with this healthy water, nutrient, rootability, microbial ecology, again, you can draw down massive quantities of carbon. The best I know, scientifically, is water hyacinths, and it can fix up to 500 tons of biomass per hectare per annum. Sugarcane can do 200 tons of biomass per hectare per annum. So massive carbon drawdown potential, provided it's got healthy soils through these dividends. So profoundly important effect. The second part of the questions was what happens when soils are anaerobic? Or could you just read that part again?
Does anaerobic conditions in paddy affect the rate of decomposition?
Right, thank you. Definitely, when you have anaerobic conditions, you don't have oxidation, because you need oxygen to oxidize, and of course when it's anaerobic, you're slowing that down. And in a sense, this is partly how these processes work. Okay, there are fungi that are actually turning cellulose, lignin into humates and glomalin, which are biochemically inert compounds. But by the simple activity of these fungi in the soil, because they're using oxygen as part of their respiration, they are creating lower oxygen partial pressures in that soil. So rather than it being 21% as in the air, the oxygen partial pressure in an active microbial soil, a high microbial life, might be 15%, 12%. And so that by itself will slow down the rate of oxidation, of carbon emissions. And we can see that there's a very clear graph. Basically, if we look at emissions, and this is percent carbon, as the soil carbon increases, you'll get a rate of carbon fixation and then it'll increase. Because at some point here, it's now 15% oxygen concentration, whereas here it was 21%. And because it's a lower oxygen, it's more anaerobic, a bigger percentage of the carbon is fixed. Okay, so yes, creating anaerobic microsites in the soil can slow down emissions. More carbon is fixed and stored. Just adding to that, you need to also, soils naturally create these anaerobic microsites because that's where nitrogen fixation can occur. Okay, nitrogen turns from gas to ammonia and amino acid, available forms of nitrogen through microbes, and they can only do it through microbes, in these anaerobic sites. So you're really creating the sites that are suitable for actually increased nitrogen, biological nitrogen fixation. But perhaps that's a complication that's too far.
Some similar question to this. Why huge jump or quick jump in yields is happening on few crops? Why not in other crops?
So say that again.
When they switch to ZBNF, only in few crops they are able to see quick jump in the yields.
Okay. Look, I don't have an absolute answer to that. You would have to look at the crop and look at what is limiting growth. See, it's very simple in a way that sunshine, CO2, water and nutrients, and that's the components that you need for the growth. And if you aren't getting a real yield response, one or more of those things is limiting. Okay, is there enough water? Is there enough nutrient? There's mostly enough sunshine, there's mostly enough CO2, but what's limiting? And you would really have to do that problem solving, that diagnostic, to say why that was occurring in this site but not on that site. It can often be, though, that as we've said over here, when we're looking at the dry season, pre-monsoon, dry sowing, that if you haven't switched on these microbial processes, you can't get the water, you can't get the nutrients, therefore you can't get growth. So these biostimulants are often critical preconditions to getting this sequence, but you would really have to look at each case.
There's a perception that where soils have been given huge doses of chemical fertilizers year after year, will those soils take more time to recover and adapt to ZBNF versus, let us say, in a tribal area where there's very little of these chemical fertilizers, so they are responding better. So I think that seems to be is that the question? That is because that's what we are seeing. In some districts the response is the yields are much better in ZBNF from the first year, second year itself. In other districts, that yield gap. So one doubt is, because these districts like cotton, chilies, maize, corn, they apply 10 bags, 12 bags, 14 bags of fertilizers.
Okay.
twice a year.
Yeah, okay.
So
No,
does that have a inhibiting
yeah,
effect?
big
That is
time. Okay.
that seems to be the question.
Yes, absolutely. I mean, if you that situation, there's a whole complex set of problems. Let's go through them. First of all, you may have oxidized most of the carbon from the soil, so that soil will be much slower to respond because it hasn't got residual carbon. Secondly, you put so much fertilizer on that soil for so long that you've basically totally killed these things, and it takes a lot longer to get established. But worse still, by having put so much fertilizer on for so long, you could have put a lot of toxins into that soil, because fertilizer contains cadmium and mercury and those sorts of toxic materials in small amounts, but continual additions creates very toxic things, and to get rid of those toxic heavy metals takes a long time, sometimes never. The other thing that happens by a lot of fertilizer additions, you also have turned that soil very acid. You know, you have acidified that soil, it may be at pH 4. And at those pHs, aluminium comes into solution, cadmium becomes more available, and so you end up with a much higher toxic, aluminium, cadmium, soil environment that really, kills plants and retards. So again, we would have to look at that soil. Nothing is totally lost. We can regenerate soils, but of course it's more difficult the more degraded.
Thank you. It's a question on impact on climate. Can the impact of APZBNF project impact climate at a larger level? And any similar program is happening in any part of the world now?
Right. So the issue of climate scales, again, varies, doesn't it? Because here we talked about, here is a single tree taking heat, cooling. So in a sense, here we have a micro site cooling effect. And that works very, very well. So you can do this at a field. As I mentioned, I live in Canberra. It's only a little city of 400,000 people. We have half of it, the older part, which has got trees, and therefore it's cooler, 12 degrees cooler on a hot day. And that's at a sort of 2,000, 5,000 hectare scale. So it can be done at different scales. At a continental scale, global climate scale, obviously it's much more complicated, but we talked about things like clouds, and of course once you induce cloud nucleation, that happens over a bigger regional area. So yes, it works at different scales. Also important to notice or to mention in terms of time scales. It will take centuries, many centuries, to remove enough carbon dioxide from the air to reduce carbon dioxide levels, because there's 750 billion tons of carbon in the air, there's 38,000 billion tons of carbon dissolved in the oceans, and the more carbon we take out from the air, the oceans say thank you very much, and re-equilibrate some carbon back on. It's a buffered system. So it will take centuries to remove enough CO2 from the air to influence climate change. But these things happen within hours. Okay, when you have transpiration, that heat is done there and it cools within hours. When a cloud is formed and goes overhead, we put the jumper on within minutes. Okay, so these are in terms of regional, but also in terms of timing, very, very much more effective. but perhaps most importantly, and this comes to the point of agency, we can influence those. We haven't got a hope of influencing the other one.
Thank you. Is there any threshold limit for carbon in the soil, just like it has in the atmosphere?
Right. Yes, very important question. The point is, are we getting to a plateau level, above which we can't hold any more carbon in the soil? Well, no, because peat soils, whether tropical peats or Arctic peats, are basically 100% carbon. Okay? So, well, I suppose there's an upper limit, 100%. But what the question is asking is not that sort of flippant response. It wants the thing, once we get much above 5, 6, 7% carbon, the relative benefits decline because we already have good soil structure, and so adding more carbon, it's not a linear response. So we've come to a plateau, and certainly it's still good from drawing down carbon, but the beneficial effects relatively become a plateau effect. But again, don't worry about it, because if you think you've got enough carbon in your soil, wonderful, we'll tell you another area of soil that needs it, and you can work there.
Thank you. Can regenerative agriculture work in soils that are by nature deficient in certain minerals or nutrients?
Can you say that again?
Can regenerative agriculture work in soils that are by nature deficient in certain elements?
Right,
minerals?
thank you. Look, the bottom line is there are 14 billion hectares of land on this planet. That is our reality. That's what we've got to work with. So it's no point complaining my soil isn't as good as that soil. It's my soil, and how do I make it better? Okay, so it's really a mindset, how do I make it better? As we've talked about, we can make it better by enhancing the availability and cycling of that nutrient. Okay, just as in a rainforest on sand dunes, we don't have to have a lot of nutrients, all we have to do is build the cycling processes. And so the answer is, yes, it's more difficult, it takes a bit longer on, nutrient deficient soils, but it's not this how good you are, it's going on the journey. You see, it's taking the first step, it's making the progress, and on a poor soil, you'll have a relatively higher percentage improvement potential. Okay, by doing it better, you can get bigger percentages improvement in yield, and yes, you just keep on going. It's like a journey. It's not, is it steep or flat? Yes. The fact is I'm getting closer to a destination.
Thank you.
Okay.
It's a lengthy question. We know that half of biomass is carbon and
Yes.
the other half
Yes.
is moisture.
Yes.
Give an example of 15-ton biomass will translate to 7.5 tons of moisture. Okay?
Yep.
Also, we know that only 1 ton of rain happened in that piece of land.
Yes.
How do we substantiate the difference in volume of moisture?
Right, very good question, and which is exactly the issues that we're analysing, but it's important to talk about it. First of all, of course, we've got to be careful. Where we've got the formula. Here we are. See, we've got C6H12O6, so quite frankly, organic matter is about 60% by weight carbon, and the rest is hydrogen and oxygen, right? So just say roughly half and half, which you're right. And of course, when we then oxidize it, we're basically bringing that water back out, and we're getting, that 6 grams of water for every gram of carbohydrate that we oxidize, because it's this water coming back. So that ratio is right about half. Now, they're asking then the question, okay, where we had the pre-monsoon dry sowing, okay, we only got, 1,000, on a hectare basis, we only had 1,000 tonnes of rainfall input, but the calculations from the yield of that crop, it should have required about 15,000 tonnes of water to grow that crop. And so we had to sit down in a forensic analysis to say, where could that water have come from? We know the reality of the crop. We were standing in it. We know that. So that's nature. That's reality. So we know it has happened. It's not hypothetical. But we've got to understand how do we explain where that other water came from. But we know it happened. It wouldn't have been able to grow without it. And in a sense, that was when we were doing the analysis, where could that water have come from? And then we looked at these different water fractions and said how much could have come from there, and then later, of course, from the dew harvesting. And so it's a bit like a detective thing. You say, yes, I have a dead body. It's a dead body. There's no denying it. Now I've got to work out, how it died and, what contributed. We basically have got, that's the reality. Now we've got to say, how do we measure how much water is being harvested from the air? Have we got methods to do that? And so our work and thinking was, yes, we need to measure that. Can we measure how much water was converted in this phase from carbohydrate to generate water? We know the physics is absolute. Can we measure that to verify it? Can we measure how much water was obtained from the soil's surfaces beyond wilting point by the mycorrhizal fungi? Yes, we can. We know it's a fact. It happens, but can we measure it? So it's now an important situation in zero-budget natural farming, but any innovation where you now have to document and quantify and study the processes involved. And it's very important that, yes, that's where we're looking. That's the frontier, but there's no doubting the reality. The crop is there. Okay, it's not hypothetical. So it is fact. We're just trying to understand better and verify what are the component roles. I hope that answers the question.
Thank you. One last question. It's a bigger question. So it talks about the degraded condition of so many agricultural lands, and also the quality forests in India are only 3%. Okay, and the common lands, no one manages that properly.
Yes.
All of the land under different management
Yes.
or departments, the soils are suffering. What strategies do you suggest in each of those cases? That is a broad question.
Yeah, well, that is, no, that is India's challenge. It's not, but look, no, it's very important. And I think we've already talked about it, isn't it? This is India, and you are in charge of India. They're not making another India, so you better make this one and regenerate this India. Okay, and if you have a lot of common land that is degraded and not being used, then that is the challenge, but also it is your opportunity, but it's also your responsibility. And what we can do, we can come and say, yes, there are very effective, natural, scientifically verified methods that you can use to do that. And for example, on your common land that is now effectively abandoned, and it may be a large percentage, driving around from Bangalore to up north, it was a lot of area. And a lot of it is covered by prosopis, which is you see as a woody weed. Yes. But of course, when we look at it, we say it's a wonderful plant because it's protecting that degraded common land that has been abandoned. And in a sense, it's telling you something because it's saying nature has selected this prosopis as the best plant to colonize that land. It can colonize the land because it has advantages for doing that. And in a sense, that is a solution, because then you say, look, here are these plants that are colonizing this land. How are they improving the land? Can I accelerate ecological soil and vegetation successions past that? You ask the question, can I use a prosopis, for example, as a mulch? You see, can I basically harvest and mulch and use it to give me green cover 365? So there's a whole lot of questions, but I would want to sit down with zero budget, natural farming, farmer groups, and we would brainstorm and design and ask questions. Yeah, what are the strategies? It's not for me to fly in and tell you how to regenerate India, but it would be basically sitting down and saying, can we apply this science anywhere, everywhere, to help regenerate and make these improvements?
My question is, see, we have been using these terminologies like, you start talking about soil sponge and organic matter. And then there is already one word like fungal hyphae. And then you have something like humus. Are we using these terms interchangeably, or do you see any independent meaning for each of these terms, and they form one after one? Like you look at soil sponge first, which lead to fungal hyphae. But how does one really understand these relationships?
They are different. They're different components of the system, right? I mean, the fungal hyphae is the fine tube that the fungi grow through the soil with. Okay? They certainly then tie mineral particles and aggregate mineral particles together to help make the sponge. They certainly, as we see here with fungal hyphae, turn what is cellulose and lignin into humus and glomalin. So they're parts, they're all parts of the one system, but they're different components. So these are the building blocks, in a sense, of the sponge, the components of the sponge. They each have their own function. So what you're saying is valid. They are all part of creating healthy soils, but I suppose we're like in a vehicle now pulling apart. Here is the engine, here is the brakes, here's the gearbox. You see, these are the components that make that whole biology of the soils function. So, okay, the whole thing is a healthy soil, and here are the different components and processes that make it work.
The impact of anaerobic bacteria in relation to soil compaction, and also the evaporation of carbon or nitrogen, oxidation of carbon or nitrogen.
Basically, the oxidation of carbon from soils requires oxygen, clearly. Okay? And then when you create anaerobic conditions in the soil, there's less oxygen, and so the oxidation processes slow down. You can create lower oxygen conditions through higher microbial activities in the soil, because then the microbes are eating up the oxygen, leaving less oxygen for the oxidation of the carbon. And this is this little graph we drew here, where initially, basically, this is the carbon fixation. I might have confused that. This is carbon fixation. So yeah, let's make this very clear. This is the carbon fixation. Yeah, that could have been. Yeah, look, come to that in a second. Okay, so there's a coming, and so initially it is relatively slow because here there is still high oxygen, right? But then as the fungal activity gets higher, there's more moisture in the soil, then basically there's less oxygen, because here it might be 18% oxygen, here it's now down to 12% oxygen, and so then the carbon fixation increases the rate. So in a sense, the rate of B and C is influenced by the oxygen concentration in the soil. Your point about compaction fits in with this, because obviously the more compacted soil, the less oxygen can flow into it readily. Okay, so you have restricted oxygen entry from the air above, so you're again more likely to create low oxygen conditions, so lower oxidation. The danger is if it's very compacted, then you won't even get roots down there, and if there's no roots, then there's no sugars for microbial life, and you end up basically with mineral soil that isn't part of the life system.
We are harnessing the water from air.
Yes.
So then energy is released back into the air during the
Yes.
condensation.
Yeah.
Can we even tap the energy also?
Can we
and-
capture the energy?
Yeah. Or if that energy, if enormous energy is released during the condensation,
Yeah.
is that going to be a harm to the mankind or some?
No, no. But look, let's go through that and do that very precisely, right? Because it's all connected, but it is important to do precise. Okay. Oh, well, actually, we had it over there partly, right? So we have basically, again, a tree or transpiration taking liquid and going into water vapor, and that takes 590 calories per gram. And then when that water vapor condenses into these hazes, these fog, dew, haze droplets on aerosol nuclei, that releases the 590 calories of energy, right? Most of it goes back up to space, because this is when it's cooler in the evenings, and then it just re-radiates back to space. So we've cooled the surface, we've transported that heat up into water vapor, we've released it to say at 3,000–4,000 meters, and most of that energy dissipates to space. But it does, some of it stays behind, so it does warm this air, right? So this air may be a little bit warmer because there was heat from there that's up there. Okay, so then these haze droplets at night time sink to the lower, because they're colder, they sink, and now we have again vegetation, and then we have these liquid droplets condensing on the foliage, sometimes running down and recharging partly the soil, right? But this is now liquid, so it hasn't actually transferred heat down. The question you ask is, can I use this energy? And I haven't got a solution for it. I mean, theoretically you could, but then again, you got much more solar energy coming in the next morning, so wouldn't it be easier to just harvest solar energy back down here, heating water or whatever? But technically, yes, you could use it to warm things, but again, it's 3,000–4,000 meters up in the air.
So one quick question is this. Today morning we have heard from a farmer that in PMDS there's no need for him to use the inoculants. So is PMDS paving a way for a new version of ZBNF without the need for these inoculants?
Right. Okay, look, this is important too, because this is this whole discussion of what the inoculum or the whole biostimulant process. And again, I can just sort of basically relate to how I understand or what I understand from it, but it would vary. So we have a seed, and we are basically putting now what you're calling an inoculum coating around that seed, with cow dung and urine. And the question is, how does it work? What does it do? And is there something? And from my understanding, this is a biostimulant, and it is not about the nitrogen or the phosphorus or calcium or whatever in there. It's not that, because it's only very, very small quantities. It works with very small parts per billion. So it's not that. It's basically, it's these biostimulants are switching on microbes, largely fungi, in the soil. So it's because of these biostimulants basically switching on and helping these fungi starting to grow. And it's then the fungi and of course the bacteria as well, and it is this stimulation of the microbial activity that is in a sense where you get the response, nothing to do with what the analysis of the biostimulant is. And so in the past, a lot of people have looked at, hey, what is they've asked all the questions here. What's the analysis of this biostimulant? How does it work? But they're trying to sort of explain things from the analysis rather than from its effect on this world down here, right? And that's why I think parts per billion of this biostimulant is effective. And as we heard this morning, basically where you have healthy systems continually growing, these activities that keep on this continually growing, they don't need more biostimulant. So there's no response to the biostimulant. Okay, but if it had been that they needed some magical compound from it, that wouldn't have been the case. So yeah, I see it as switches, this is the word, I see this as switches rather than additions. Okay? It's not additions, it's just switching biological processes on.
So, a big thanks to Walter. And it's been such a privilege having you and speaking to us virtually the whole day. And all of you are really, I would say, I'm the luckiest person because I've been hearing him for the past 1 week. But all of you are hearing him for the first time are really privileged. And it's a great learning to all of you. I would also like to thank Anne-Sophie and Didi, Sudhakar, Polly, Susan, the FAO team. And of course, a big round of applause to all of you.